Alright, so let's talk about impulse. Impulse is defined as the change of momentum. Both momentum and impulse are measured in units of kilogram meters per second. We can expand this out. The change in momentum would be the final mass times the final velocity minus the initial mass times the initial velocity. Another way of talking about impulse is equal to the force times the time the force was applied. So we have two main equations for impulse, which is very useful. So let's do an example. Suppose a 5 kilogram box increases its speed from 10 meters per second to 20 meters per second in 2 seconds. How much force was exerted on the box to cause this increase in velocity? So we can combine these two statements. So combining these two equations, we get that the change in momentum is equal to force times time. So the mass is constant, doesn't change, is 5 kilograms. The initial velocity is 10 meters per second. Final velocity is 20 meters per second, and the time is 2 seconds. So we have change in momentum is equal to force times time. That would be mass times final velocity minus mass times initial velocity. It's equal to force times time. Because the mass doesn't change, we can factor that out. Mass times the change in velocity is equal to force times time. And since we're solving for force, we can divide time on both sides. And we end up with the fact that the force equal to mass times change in velocity over time. Mass of 5 kilograms times 20 meters per second minus 10 meters per second over a time of 2 seconds. So that ends up with 5 times, so 20 minus 10 is 10, so 10 times 5 is 50 kilogram meter per second divided by 2 seconds. And that's equal to 25 kilogram meters per second squared, and that's the units of newtons so 25 newtons. Now, we could have also, to see where this formula comes from, let's think back to kinematics. So one of the 4 kinematic equations, so the only thing we're not given in this problem is distance. So if you remember back to the kinematic equations, one of them does not have distance, and that would be this equation. Final velocity is equal to initial velocity plus a times t. If we were to, I'm going to use an I instead of a not. So if we were to move this over, Vf minus Vi is equal to AT. And if we were to divide by t, we get Vf minus Vi over t is equal to, actually, let me back up and just show you. So if we were to multiply both of these equations, both sides of this equation by mass, so we have Vf minus Vi is equal to AT. If I were to multiply the entire equation by mass, I end up with mass times final velocity, mass times initial velocity, and mass times AT. And from Newton's second law, F is equal to ma. This can be replaced with F. So we end up with F times t. This is momentum, so this is the change in momentum. So we have change in momentum. In this example, the mass stays the same. So what we have, we can factor this out, mass times change in velocity. It's equal to F times t if mass is constant. So this is just another way of using the kinematic equation. It's just that we have our own formula and we call F times t impulse. So let's do a few more examples. Suppose a 50-kilogram object is traveling at 25 meters per second. How much force is required to stop the object in 5 seconds? So we can again use our equation. Change in momentum is equal to force times time. Remember, a change in momentum is final minus initial. So you have mass. So change in mass times velocity is equal to Ft. Since mass doesn't change, we can factor out the mass from the change sign. So we have mass times change in velocity is equal to F times t. And so we have mass times final velocity minus initial velocity is equal to F times t. And we can divide by t. And we get F is equal to mass times VF minus VI over T. So that would be 50 kilograms times, so the final speed is 0 meters per second, minus the initial speed, 25 meters per second, divided by a time of 5 seconds. And we get a total force of negative 250 newtons. This negative indicates the direction is opposing, opposite to that of the object. We're assuming that the object initial velocity is positive. Thus, in order to make it slow down, we have to apply a negative force. All right, let's try another one. Suppose a 10 kilogram object is moving at 5 meters per second. A force of 20 newtons is applied for 3 seconds. What is the box? What is the object's final velocity? So, force times time is impulse. So it experiences an impulse of 20 newtons times 3 seconds. So 60 kilogram meters per second. We have change in momentum. So m times VF minus m times VI. Since the final and initial velocity mass is 10 kilograms, I don't put the subscript because it's the same mass. That's equal to force times time. And we're solving for final velocity. So we move this over to this side. Mass times final velocity is equal to, my pen's running out. So force times time plus mass times initial velocity. And then we divide by mass. So final velocity equal to force times time plus mass times VI divided by mass. So force times time, 20 newtons times 3 seconds, that's 60 kilogram meters per second, plus 10 kilograms times the initial velocity of 5 meters per second, divided by 10 kilograms. So 20 times 3 plus 10 times 5 is 110. Divide by 10 is 11. So 11 meters per second is the final velocity. So it goes from 5 meters per second to 11 meters per second. All right, let's do another example. Suppose a 10-kilogram box is traveling at 20 meters per second and encounters an opposing frictional force of 5 newtons and slows down to 5 meters per second. How long was the frictional force being applied to the box? So, mass, 10 kilograms. Initial velocity, 20 meters per second. Final velocity is 5 meters per second. Frictional force is always opposing, meaning it's always in the opposite direction of motion. So if we're letting the velocities be in the positive direction, then the frictional force is going to be opposite. And we indicate an opposite direction as being negative. So it has a frictional force of negative 5 newtons. And we're asking how long in reference to time, so we're trying to solve for time. So mass times final velocity minus mass times initial velocity is equal to F times time. So this would be 10 kilograms times 20 meters per second minus 10 kilograms times 5 meters per second equal to negative 5 newtons times time. 10 times 20 is 200 kilogram meters per second minus 10 times 5 is 50 meters per 50 kilogram meters per second. And a newton is just kilogram meters per second squared times time. 200 minus 50 is 150 kilogram meters per second. It's equal to negative 5 kilogram meters per second squared times time. Divide by the force. And made a mistake. The mistake is 20 is the initial. That should be 20. Final is 5. So 5 times 10 should be 50 here. 10 times 20 should be 200 here. 50 minus 200 is negative. So we should get negative 150. This is why putting in units and signs always helps. Because time is always going to be positive. Time has no direction, we usually say. It's a scalar, so it shouldn't have a negative sign. So negative 150 divided by negative 5. It's 30. And kilograms cancel out with kilograms. Meters cancel out with meters. Seconds divided by per second divided by one of the per second squareds. And we're left with a per second divided by a per second, which flips over to seconds. It is very easy to plug this into the wrong variable. Final is 5 meters per second. Always double check that you're inserting this into the correct variable. Very easy to make a mistake. Suppose an impulse of 50 kilogram meter per second was applied to a 5 kilogram box. You can always assume, unless stated otherwise, mass is constant. The question is, what is the change in velocity? I.e., what is Vf minus Vi, or equivalently, delta V? So we have delta P is equal to J, which is delta mv equal to J, and mass is constant. We can assume that. So we get mass times change in velocity is equal to the impulse, and we can divide by mass to get our change in velocity. So the change in velocity is equal to your impulse divided by the mass, if mass is constant. So the impulse is 50 kilogram meters per second divided by 5 kilograms, and that gives us 10 meters per second. So we will increase by our speed by 10 meters per second. So if the box was moving 20 meters per second, this change in velocity indicates that we will be now moving at 30 meters per second. All right. Let's do another example. A 5 kilogram box experiences a frictional force slowing it a frictional force slowing it down to a stop. If the frictional force had a constant magnitude or value of 10 newtons and was applied for 2 seconds, what was the initial speed of the box? Initial velocity of the box. So, mass equals 5 kilograms. Initial velocity is unknown. Final velocity, since it's coming to a stop, final will be 0 meters per second. Again, frictional forces are opposing, so the frictional force would be negative 10 newtons. We're going to assume that the initial velocity was in the positive direction and the frictional force is in the opposite direction and negative. And our time was 2 seconds. So, mass times final velocity minus mass times initial velocity is equal to force times time. There's 2 ways you can go about doing the algebra here. So if you're solving for a variable, one strategy is move everything to the other side. And if you do it this way, it requires more steps. So if you just move everything to the other side, you'll all wind up with doing this. So getting this by itself, we would move this to the right. So if we move this to the right, that'd be negative mass times velocity is equal to Ft minus mvf. And to get rid of the negative, we have to multiply the entire equation by a negative 1. So this becomes positive. Bi is equal to negative Ft. A negative times a negative is positive. And you get like this. Personally, whenever I see that my variable has a negative, I will move this to the right side and then this come over here, winding up with Vf minus Ft. Then moving this to the right side, that would be a positive Vi. Same thing over here. And then we can rearrange this as mass Vi equal to mvf minus Ft. I just swapped these sides. And then divide by mass. Vi equals mvf minus Ft divided by mass. And I can pull this out, just showing you how to clean up some algebra. So that's divided by mass minus Ft mass. So we have this numerator over this. We can break it up. Mass divided by mass cancels out. And so we get initial velocity is equal to final velocity minus force times time over mass. So the initial velocity, or the final velocity, is 0. So that cancels out, leaving us with force times time over mass. So that'd be a negative times negative 10 newtons times the time of 2 seconds divided by a mass of 5 kilograms. Negatives cancel out. 10 times 2 is 20 Newton seconds divided by 5 kilograms, which winds up giving us 4 meters per second. So the box was initially moving at 4 meters per second, encountered a frictional force of 10 newtons for 2 seconds, and slowed down to 0 meters per second. Let's do one more example. So recall that impulse is simply equal to the change in momentum. Suppose a 5 kilogram box is moving to the right and bounces off a wall and ends up moving to the left. Let's say the box is moving to the right at 10 meters per second and ends up moving to the left at 10 meters per second. What is the change in momentum? So remember that momentum has a direction, it's a vector. Usually if I don't indicate directions, it's alright to just use positive and negative to indicate directions, and usually we'll kind of ignore direction altogether as it doesn't matter. But if I specify directions, you must in your answer also specify direction. So what we have is a box. It's initially moving at 10 meters per second. And then it hits a wall, bounces off. So it hits the wall, and it bounces off and is moving at 10 meters per second to the left. When it hits this wall, a force is going to be applied to it, or an impulse, technically. And this impulse is going to be pushing the box to the left. So I'd expect my final answer to have the direction of the left because that's whatever direction of the force being applied to it. The box exerts the force on a wall. Newton's third law equal, for every action there's an equal and opposite reaction. And the impulse is going to be on the ball, so I'd expect the impulse to be back on the wall, pushing it back. We can temporarily set positive and negative, so right be positive, left be negative. Do our math. So we have mass times final minus mass times initial. So the final, since left is negative, be negative 10 meters per second, and that'd be 5 kilograms here, minus 5 kilograms. Initial was positive, so 10 meters per second. So that'd be negative 50 kilogram meters per second minus 50 kilogram meters per second. And we end up with a total of negative 100 kilogram meters per second. So our final answer is thus the change in momentum delta P is equal to 100 kilogram meters per second to the left. In scenarios like this, when we encounter a bounce, we often think of the wall as being immovable. In which case, because the wall is attached to the ground, it's seemingly as if momentum is created out of nothing. There's a change in momentum. So let me write this down. So momentum, linear momentum specifically, or really all momentum, is constant when there are no net forces, no external net forces. So even if we include the wall as part of our system, there is going to be an external force. The ground itself is pushing on the wall, keeping it from moving. So some of the momentum is extracted from the earth or put into the earth, and we can't keep track of it. So in this scenario, there is a external force. It's coming from the earth that's pushing on the wall, that pushes on the box. So momentum is seemingly not conserved because there is external net forces being applied that we can't keep track of. In a perfect scenario, or an elastic scenario, meaning that, so in an elastic collision, there is no loss of energy, kinetic energy due to heat. Bounces perfectly reflect momentum back. So basically, if a box, let me do this. In a perfect elastic collision, if a ball is moving down with some momentum, and it strikes the surface, it's going to bounce, and it's going to bounce in the same way to conserve kinetic energy. Kinetic energy is not a vector; it has no sign or direction. So if this was moving down with 1/2 mass times velocity squared, the square on the velocity gets rid of the sign or direction. This is going to have to stay mass times velocity squared. So that means since the mass doesn't change, in order for these two, for the kinetic energy to be constant, the velocity doesn't change, and hence the momentum doesn't change. The momentum seemingly flips direction though, so there is a change in momentum, but the magnitude, meaning the value of the value portion, the number, doesn't change. The sign does. There is a change in momentum, like in this scenario. There's actually, it's having 50 kilogram meters per second. So the total momentum here is 50 kilogram meters per second to the right. It does change by negative 100 kilogram meters per second. So there is a change in momentum when you look at the sign and as a vector, but the magnitude or absolute value, just the number portion, doesn't change. So the absolute value, ignoring direction, doesn't change, but there is still a change in momentum because there was a force applied for a brief period of time. The velocity, I should say the velocity's magnitude, or to be more accurate, speed doesn't change, meaning the absolute value of the number, but the sign and direction does. So here, again, it's going, so if I were to ask you, what's the change in velocity here? 10 meters per second to the right, going to 10 meters per second. Well, the change in velocity was negative 20 meters per second. However, the absolute value, or magnitude, is 0. just the number by itself is 0, but when we include direction, we get an actual value. I'm going to post homework on Google Classroom. If you got a printer, print it out. If not, you can get a paper copy when you come to class tomorrow. My plan is tomorrow do a test review, and Friday we'll have a test.